Tutorial for today. Now this tutorial actually is not very long. If you look through, it's actually just 5 questions. So like problem 1 is mainly is a refrigerator question, but an ideal one. While the second one is actually a refrigerator, but the actual one. Then problem 3 and 4 also same stuff. You see this is actually the heat pump, but the ideal heat pump. And the last one, and the fourth is actually heat pump actually. Then the last one, we have a cascade. I think it's an ideal one. Okay, so for today, I will discuss the 2 actual ones. Ideal one, I will just leave it for you as practice because ideal is everything is quite fixed. I'll discuss the 2 actual one, then we will briefly look at the cascade one. Then that will be all. Hopefully we can finish 5 minutes earlier because I need to run to block P for Viva. Okay, so let's look at problem 2 then. Like I said, we will look at the 2 actual one. Okay, so we have problem 2. So as I mentioned in class, if the question never say anything about being ideal, you cannot assume it is an ideal cycle, even if it is. Okay, there are cases where it might be ideal, it might be not. Like this morning when we discussed the exam question, you will see that I did set like state 3 to be ideal, but the other one is not. So what's important is that you must refer to the question, see what are the information given to you here. So here problem 2, a commercial refrigerator with R144A as the working fluid is used to keep the refrigerator space at negative 30 degrees Celsius by rejecting its waste heat to cooling water that enters the condenser at 80 degrees Celsius at a rate of 0.25 kg per second and leaves at 26 degrees Celsius. So again, a lot of information here. Refrigerant enters the condenser at 1.2 megapascal and 65 degrees Celsius and leaves at 42 degrees Celsius. Inlet state of the compressor is 60 kilopascal, blah blah. So a lot of information are given actually. So they are also not state labeled at the diagram over there. So first, determine the quality of the refrigerant and evaporator inlet. Then B, refrigeration load. C, COP and theoretical maximum load. Okay. So I will start by just sketching the TS diagram. So this question doesn't really tell us anything about the cycle. Okay, I mean it doesn't really tell you exactly, but it does give you all the information there. So this one, let's say, yeah, we know that there's always 2 pressure level here. Then 1.2 megapascal, 60 kilopascal. So these are the 2 pressure levels. You can see from the question as well. So these are the 2 pressure levels. So now, based on the information there, if you just look at state 1, state 3, if you go through the table, let's say, if you really check, you will see that these are at superheated state as well as a compressed liquid state. So this question didn't really ask you to draw, so that's fine. It's just that I'm just drawing this to show how the thing goes. So maybe I write down the information first. So it enters the condenser at, oh, that's the water. So this one we don't care about that first. At the rate of, and this at, so the refrigerant enters the condenser at 1.2 megapascal. So we know that P2 equals to P3 equals to 1.2 megapascal. T2 is 65 degrees Celsius. T3, 42 degrees Celsius. So these are all given to you. Then P1 equals to P4, 60 kilopascal. we know that T1 is -34 degrees Celsius, and the compressor has a net heat of 451. So that is actually something new. We leave it for now because it is not something that I actually taught you, but you can also see the diagram there. We will talk about it later. Alright, so here this is obviously an actual cycle. So if you are to draw the actual cycle, it looks something like this lah. So here this is this is 4, 1, 2, 3. Not sure if we need the isentropic version, but we can just write it down. Most likely we don't need it because the question doesn't. Yeah, based on the question, most likely you don't need it because you do have some other information there. Not sure yet, so we just write it down. And we know that here this is, so this is put in, this is QH, QL. Okay, so there are other information in the question, just like the exam. You will see, so we go back to the first question. So this refrigerator is keeping the refrigerator space at -30 degrees Celsius. So meaning at this space, this is TL equals to -30 degrees Celsius. Let me move this a bit. So QL, so this comes from here. So basically we are taking this from this space. Makes sense, right? So TL is where we are cooling down. Okay, now at the TH actually we do have one more thing here. So if you even if you don't understand the what's written there, you can look at the diagram as well. So we are actually using water to cool down the refrigerant at the condenser side. So we have a water here, so pretty much something like this. So let's say you have water. So this water will come into the condenser. And from here we reject QH to the water. So the water changed from 18 degrees Celsius to 26 degrees Celsius. Okay, so I think we pretty much wrote down everything. Besides, okay, there is a net heat Q in to the compressor, which is 451. So this is something new here. Otherwise, yeah, pretty much settled. So first we need to find the quality, then refrigeration load, COP. So these are all pretty standard things. Let's see. Okay, we need the quality at the entering the evaporator or at the evaporator inlet. So meaning number 1, we are looking for X4. So just like the exact question actually so happened. So how do we find X4? So what can we find first to find X4? Don't know what to do here. Actually, this is actually the same question as asked this one for those of you who look it there. Okay, so if temperature T4, how do you find T4? Actually, T4 is just T saturated at 60 kilopascal. Yeah, so there isn't much use there. Okay, so standard way of solving this kind of question, if you don't know what to do, ignore the question. Find all the H first. Then you see what you can do. So what do I mean by find all the H? You can start from, so this is not the proper, this is the proper steps to solve this kind of question, but not the proper way to find X. As in, we are not looking for X directly here. We are just solving, so let's say in this case, all of you don't know what to do. Just start from step 1. You look for them one by one. You look for H, all the H. Because you need the H eventually, like I mentioned in the class. So we know that P1 is 60 kilopascal. T1 is -34 degrees Celsius. So this one, if you go to the superheater table, most likely is a superheater vapor. You can get H1. Okay, you have enough information for this. So after that, we go to state 2. We know that T2 is 1.2 megapascal. Yeah, so in this case, right, actually 2s has no meaning here because you are actually given T2 as well. So whatever information that is given to you in the question itself, they are always the actual information. So meaning if you, let's say, based on this 1.2 at 65, this is always 2 or 2a. It will never be 2s because 2s is the ideal one. So unless the question says this is an ideal cycle, otherwise information that's given to you are always the actual for the actual cycle. So from here, same thing, you can find H2, right? Then we go to state 3. So for state 3, same thing, T3 is 1.2 megapascal. T3 is 42 degrees Celsius. So if you check the table, you will see that this is a compressed liquid or a subcooled liquid. So for this, how do you get the value for H3? Yes. So you apply what value and temperature? Saturated liquid. This one here. Here. Okay. So you approximate it to saturated liquid value at the temperature. Don't use the pressure value because it is compressed liquid at that stage. Okay, then we are done with state 3. Then state 4, what do we do at state 4? We know P4 is P1, which is 60 kilopascal, but then that's all. Uses this information for now. No, T is not the same as T1 because T1 is here, is superheated. Like T1 is here, right? It is a superheated state. The T for 4, because 4 is a mixture, so T, let's say T4 lah, is always T saturated at 60 kilopascal or at P4. So this is not useful because they are both dependent value. Dependent value can't help you to do anything. You want independent value 2. So you need one more thing. The one more thing is what you did in your lab. Okay, by the way, lab, you did something wrong here. You check what is it for this one. Actually, yeah, it's your group because I was wondering whether the tutor didn't mention it, but then somehow when I look at the MH one, they did that correctly. So for you guys, or maybe I just talk about it here, since we are at this part. You know your pH diagram. You draw this right. We don't care about this point. I mean, it doesn't look exactly like this, but you want. This point you got no use one. So for you, right, whether it is the indicated or the actual one, you are still using these 2 points. You don't use the saturated point. The only thing that changes is this point only. Okay, the 1 and the 2, they are all the same point. Because because all your p-values you get from the experiment. So technically speaking, you don't really have a theoretical value. They are just the indicator value, as in what you are expecting from this system. That is the COP. Then the actual one, then is the one that you draw one more time for the 4. That's all. Well, 1, 2, 3 supposed to be the same value. But anyway, based on here, remember, H3 equals to H4 prime. So meaning, this one is also H3, H4 equals to H3. Okay, it's the same thing. So H4 equals to H3. Then now you have the H3 value, H4 value. Then you can calculate H4 based on, we know that H4 equals to HF plus X4 HFG. So from here you can get X4. Okay, so now that you get H4, then you get X4. So pretty much you got all the H in this case. Then we come back to the question. So B, you need to find refrigeration load. Okay, so this one is actually A. So we need to find a refrigeration load. So refrigeration load, very straightforward. Refrigeration load is just basically how much heat you are taking or how much you are cooling down, which means you are looking for QL. So QL is just m dot H1 minus H4. Even though I say it is just H m dot minus H1 minus H4 lah, but we look better at the question again. Okay, I didn't write it down, but we look back at the question again. Is the mass flow rate of the refrigerant given to you? Because this mass flow rate is supposed to be the refrigerant mass flow rate, right? Because we are talking about the R134A here. The H1 and the H4, they are all the R134AH. So you need the mass flow rate of the R134A. But is that given in this question? So this is actually a tougher part here. So we have one information that we are given, but we don't really know in a sense that we haven't used it yet, which is the cooling water. Okay, so the cooling water, you see, so now we need to go to the cooling water first. So for the cooling water, we know that it enters at 18 degrees Celsius and it leaves the condenser. So this is the condenser at 26 degrees Celsius. Mass flow rate of the water is 0.25 kilogram per second. So that's what we know, right? So, and based on this question here, you can see when we draw this, actually it's the same thing, I just put it there. So you can see that the change in the temperature is actually due to the QH. Right, so this is QH. So from here, we actually can create an energy balance equation here, which is m dot, don't use Cp delta T because it won't be as accurate, or So for water, we try not to use Cp value. So instead, we will use H. Since they are both cooling water, meaning they are in pure liquid form. In liquid form, we can say that it is just a compressed liquid, which means it will be F at 26 degrees Celsius minus HF at 18 degrees Celsius. And we further expand this, so this will become m dot of the refrigerant, H2 minus H3 equals to m dot, HF at 20 degrees Celsius, sorry, 26 degrees Celsius, minus HF at 18 degrees Celsius. So you need to go to the table to look for, so we have H2 and H3 from the previous section, so now you need the HF of the water. So this is a water, or cooling water. But don't get confused between your table, because this will be the table for H2O. So from here, you can get the mass flow rate of the refrigerant. Sorry. Then you sub this back into the refrigeration load equation to get the refrigeration load. Can you understand what I'm doing here? No, I'm not asking. Let's say if I give you this question, can you do or not? No, I'm only asking. Do you understand what I am doing here? Different type of question. Okay, so at the condenser, so usually, right, when we do here, let's move here. So usually, right, at this section, we are just throwing it to some ambient. So now instead of an ambient, we use cooling water. That's all. Okay. So then, now, so it's the same thing lah. So we are rejecting the heat from the cycle to the water. Okay. So the water, when it passes through, temperature increases. So the heat from the refrigeration system should be equal to the heat received by the water. Okay, so this is the case. So this is the heat from the cycle equals to. So this one usually we will do MC delta T, but I said water usually we don't use MC delta T lah. So instead of using MC delta T, we use M delta H. And normal, so water at 18 degrees Celsius, so this cooling water, you can imagine it as just normal water. So normal water, the liquid form is always compressed liquid. So same thing as the previous one. So if it is compressed liquid, then the enthalpy will be HF at 26 degrees Celsius, HF at 18 degrees Celsius. So you equate these two, so we expand it again. Then from here, you have this value, you have this value. This is given, you can find these two values. Then you can find mass flow of the refrigerant. Then you sub back in, then you can get refrigerant. Okay, so then we move on. See, now that you found refrigeration load, the problem here will be, so C also got a bit more work here. What is the problem here? So now, COP is QL over work in. This is generally the equation, right? But here, there is again one small issue, which is this. This one cannot zoom in. So if you look at the compressor here, do you see that there is a Q in the compressor? So which means that for this compressor, right, instead of usually we just say work in equals to M dot H2 minus H1. But this time, actually we have this. Makes sense, right? Because this is the overall change in the energy, or that result in the change in the temperature, if you can think about it that way. So this overall change in the energy, usually when we say adiabatic compressor, then the whole change in energy is due to the compressor. But now, because the compressor is also absorbing heat from the surrounding, then the resulting change in enthalpy, you need to add on the heat. So which means in this case, you need to minus off the Q in that is given by the question, which is 450 watt. Then only you can find the actual work in this case. So then you sum it into COP, then only you can find the actual COP value. So this question, right? So let's say if you decide to find things through like energy balance, remember we can always write QL plus work in equals to QH. So in this case, right, let's say if you decide you need to add another Q in over here, because that is the overall change in the energy. But we don't take the Q in into consideration for our COP lah. Because in a way, when you put in the QL and work in, you have considered the Q in. So we don't need to care about the Q in when we calculate COP. It's just that in case you want to find balance in this way, then you need to remember that there's a Q in and energy inside. Okay, so lastly, we need to find the theoretical maximum refrigeration load for the same power input. So, meaning the last part is that you need to find the theoretical maximum load. You want to find the QL maximum. So, meaning by theory, so if logically speaking, this cycle is what is the maximum load that it is supposed to be able to remove with the same work in, meaning your COP needs to be the maximum, right? So same work, you can see the keyword is also same work in. Now, so if you use back the same work in, you are supposed to get the maximum COP also. Makes sense, right? So what is the maximum COP? It will be the reverse Carnot version. Always remember the theoretical maximum value is always the Carnot version. So based on the Carnot version, which means you can use this equation to find the maximum Carnot, the maximum COP. So for this question, so TL is negative 30 plus 273 for TL. One last question for this particular one. Then what is value of TH? This is considered a hard question. I mean, especially like this is the first time we are doing this in the tutorial. So TL very obvious. If you come back to this question, TL is just negative 30 degrees Celsius because that is the refrigerator space, the space that you are cooling, keeping the temperature at. So usually, like I mentioned just now, usually our TH will be, let's say, ambient. So then let's say if ambient is 27, then you put in 27 plus 273, which is 300 Kelvin. But in this case, you actually have a water, cooling water. And this cooling water will have two temperatures. So which temperature are you going to use? Why? Why? Why?
Before the heat included.
Yeah, why? I'm asking why you choose 18?
Why? Before the energy is transferred into the water.
I mean, the answer is correct lah. This is the lower one. So you think about it this way. Usually, you have condenser. You reject heat to a reservoir, right? So let's say your ambient is 27 degrees Celsius. Technically speaking, after you reject heat to the reservoir, it will increase a bit the temperature. It's just that not noticeable. That's why we call it reservoir. Then, so the 27 here is the original temperature of that space. So same thing here. So like I said, I think he knew why, but then he cannot put that into words. So same thing. 18 is the original temperature of the water. 26 is after it has absorbed the heat. So the water that you supply will always be at 18. So that 18 is your TH because that is the temperature that you are rejecting heat to. Okay, so yeah, so here it's just that. So you need to settle what's TH, what's TL, then from there you sub in the value, you get the maximum COP, multiply by the work in, you will get the maximum theoretical, the maximum refrigeration load. Okay, I think I will discuss cascade this one. Not enough time for two questions. Alright, then we quickly go to problem 4. Okay, so problem 4 is another actual question, but this time it's a heat pump. So let's take the question. So a heat pump using R134A heats a house by using underground water at 8 degrees Celsius as the heat source. So the house is losing heat at a rate of 60,000 kilojoule per hour. The refrigerant enters the compressor at 280 kilopascal at 0 degrees Celsius and it leaves at 1 megapascal at 60 degrees Celsius. And it exits the condenser at 30 degrees Celsius. So if you just look through the question, it is actually a pretty straight normal question. So you are just asked to find the power input, the rate of heat absorption from the water, and lastly, the one later we see. It's actually a question that we asked in as one of the example as well. Okay, so as usual, I will draw the TS diagram first. This is also an actual one. Okay, so what do we have here? So 1, 2, 3, 4. So we have work in, we have Q, so we have QL. So this QL comes from underground water. So you have underground water TL equals to 8 degrees Celsius. And it rejects heat to QH. So this QH is to a house. We are warming up a house here. So you are told that this house is losing heat at, so Q loss, let's call it, 60,000 kilojoule per hour. Okay, so what else we know here? So refrigerant enters the compressor at 280 kilopascal. So this is 280 kilopascal. One is 0 degrees Celsius. I just write it up. So P1, P2 is 280 kilopascal. T1 is 0 degrees Celsius. And it lives at 1 megapascal and 60 degrees Celsius. Sorry, this is P4. So P2 equals to P3 is 1 megapascal. Then T2 is 60 degrees Celsius. So once again, we don't really need the isentropic efficiency here. So refrigerant exceeds the condenser at 30 degrees Celsius. So we also know T3 is 30 degrees Celsius. So determine A power input to the heat pump. So generally speaking, the first part of this question is exactly the same as the previous question, whereby you find state 1, state 2, state 3, state 4, based on all of this information. So this one I won't waste too much time on talking about it anymore, I'll just write them down. So this one we know this and this, you can get H1, you don't need S1 as well because state 2 was given to you. Now in the actual case, so in the actual cycle case, in general you only need S1 if you do not have enough information at state 2 and you are given isentropic efficiency. So either one of them. So if there's no isentropic efficiency, mostly you don't really need the S2. You don't need the 2S value, meaning this one. So if you draw this, by right there is a 2S here. But here we don't need it because we are not getting the isentropic efficiency involved. So from here you get H2, then state 3, so state 3, we have P3 equals to 1 megapascal. So exactly the same as the previous question here. Okay, so A, we want the power input. So power input is H2 minus H1. So once again, just a reminder to you, if the question never mentioned any term like specific or per unit rate, we always want them in terms of like the full term, like they say the capital letter version. So which means we need mass flow rate in this case. So I just write B first. So B, you want rate of heat absorption from the water, actually it's just QL. Technically speaking, it's just H1 minus H4 also. So you can see that both A and B are actually pretty straightforward once you know how to find out the H. The only issue here is we need the mass flow rate of the refrigerant, actually just like the previous question. So based on here, how can you find the mass flow rate of the refrigerant? What information do you have here? QH? What is QH? Why? Why? Yeah, in order for you to maintain this space at a fixed temperature, Q gain must be equal to Q loss. Because if QH is higher than Q loss, then the house will just keep getting hotter and hotter. If the other way around, then you will still keep getting cooler, cooler, then your heat pump is useless. Okay, so in that case, so which means that here we know that QH is equals to Q loss, which means this is equals to m dot H2 minus H3. So QH value is just 60,000 kilojoule per hour. So you need to convert it to kilowatt first. So be careful of this. Then this is just H2 minus H3. So you can get mass flow rate. So you can get mass flow rate here. Once you get the mass flow rate value, you can sub in here. You can get work net E. Just go and do. Okay, so once you get this, now technically speaking, QL you can find it that way, or you can just say QL is equals to QH minus work net work in. So this also work because you found the value. So because you have the value of QH, you have the value of work in from A. So technically speaking, you can just find the value through this. So both of these should give you the same answer. You can choose either one of them to use up. Okay, let's quickly look at the last part. Okay, so here very fast. So then C, the increase in electrical power input if an electric resistance heater is used instead of a heat pump. So in a way, you can see what is the answer there also. Now, so what happened if instead of having a heat pump, you just use a resistance heater? So your house, you add a coil here. So resistor heater. So this resistor heater, you need to supply heat. And resistance heater usually will have pretty good conversion rate because we are just converting electricity to heat, which, as you know, heat is the easiest form for us to convert to. So which means, let's say if you want to do the same amount of work, I mean, you want to heat up the same room, which means that this electric power should supply how much energy? 60,000 kilojoule per hour, which means it needs to supply QH. So the question asks for increase in electricity power. Actually very straightforward. It's just QH minus work in, which is actually QL. So now what we are just trying to say is, if you are using a heat pump, then you are saving this much power because you are taking this power from the underground water. Basically, you are taking that source from outside, then you only need to supply this much in order to do this much work. So if you are using a normal resistance heater, then of course you don't take heat from other places, you only have electricity power. So it will be the full term, which is QH. Then the increase is the QL. So in country like us, then using resistance heater will be more worth it because you don't really need this thing all the time. Like if you have 4 seasons, then yeah, heat pump will save a lot more power in comparison. Okay, so here, does anyone feel this? No? Okay. We actually nothing much to discuss lah. We just quickly look at cascade lah. So problem 5 is just a cascade one. You can try, but the method is actually more or less the same. So we have 8 minutes. Like I said, I need to leave. Yeah. So we have a cascade here. Pretty much, you can see. You are told that the cascade refrigerator works between these 2 pressure. Now, when we say that it works between these 2 pressure, right, it will always be the lowest and the highest. Okay, so you can see. So each of them works under ideal cycle, and the heat transfer takes place at 0.4 megapascal. So this one, if you are to draw this. Then you actually have 3 pressure level. So the highest will be 0.8 megapascal. The lowest 0.14 megapascal. Then you have an intermediate one, which is about 0.4. About we don't care, I just say 0.4 lah. So you have 2 ideal cycles. So actually, it's just ideal one. You just connect them. That's all. So now how you want to label, right? To be honest, if the question doesn't really give you any number, you can label any way you write. I will just mark accordingly. But let's say if the question gives you the number, because sometimes I give, and then the number is not exactly the same as what you learned in class, please follow, okay? Don't give your own number, then it will be a bit confusing. So anyway, so here you can just call this cycle A, cycle B. So you are given mass flow rate of cycle A is 0.24 kilogram per second. That is the upper cycle. Then you need to find mass flow rate of the lower cycle. So this one actually pretty much everything you have learned. So let's say you look at cycle B, H1 is just Hg at 0.14 megapascal. Then, but to find H2, then you need to find S2 equals to S1 first. So this one you refer back to your notes lah. But because for ideal cycle, it's all just very straightforward. So you find S2 equals to S1, then you can find S2. So H3 is just HF at 0.4 megapascal. Then H4 equals to H3. So for cycle A, you repeat. H5 equals to Hg and 0.4 megapascal. Then you find S5 or S6 equals to S5. Then you find H6. Then H7 is Hf at 0.8 megapascal. Then lastly, H8 is equals to H7. So from here, you can find all the H. So now you need to find mass flow rate of the refrigerant through the lower cycle. So we know that they exchange heat between the cycle. So here, mass flow rate of A multiplied by, so mass flow A is the one rejecting heat, absorbing heat. So this will be H5 minus H8, A, H2 minus H3. So from here you can get, this is B. So from here you can get mass flow rate of B. Okay, so B asks for rate of heat removal from the refrigerator space and the power input. Now, heat removal, even if you have 2 cycles, is only just that 1 QL, okay? Just like QH is also here. Whatever that happened here, we consider them to be in equilibrium, so we don't care. We only use the middle part for this particular purpose. And this is your work in maybe A, this is work in B. So here B is simply rate of heat removal, which is QL, is MB H1 minus H4. Then work input is actually work in A plus work in B. Then MA H6 minus H5 plus MB H2 minus H1. Then lastly is COP. COP, you just use this two. Okay, so basically this way. The cycle B and A and B, these two things, they will refer back to how we do for ideal cycle. Ideal cycle has a very fixed method to find all the states, so there shouldn't be any issue. You can check the notes. So this cycle, the only catch here would be this one. Be careful here. There are 2 compressors, so you will always have 2 work in. But QL and QH remain as just 1.